Today I'll be talking about the creation of a simple electric motor, using minimal materials to convert electrical energy and magnetic fields into magnetic force, causing the screw to spin. In this lab, we need to build a simple electric motor, provided a 1.5 volt battery, a 14.5mm by 4mm dipole magnet, a 30mm screw and a coated wire. Once this motor was successfully constructed, we tested the result of flipping both the battery and the magnet in the setup independently, and importantly, the function of the system without the magnet. After that, a series of measurements could be taken to estimate the motor's hertz, or revolutions per second, using slow motion footage to individually count each rotation. This motor demonstrates how magnetic force can propel objects in a direction. The direction of the force can be found using a useful trick in physics known as the right-hand rule, a diagram of which is displayed here. When paired with a diagram of our electric motor, it can help us to determine the direction in which the motor will move, as the applied force's direction switches when the polarity is changed. This can be done by flipping the battery or reversing the pole of our magnet. This is the basic concept of an electric motor. To make such a motor, you need a magnet, which will create a magnetic field resulting in the screw spinning. This is partially due to the small point of contact, which reduces friction. Full motors are more complex, utilizing a number of electromagnets and conducting wires, in combination with curved permanent magnets and brushes, allowing the electromagnets to spin freely. A similar concept can be seen in our motor, in which the wire brushes against the magnet to complete the circuit, rather than being permanently connected and impeding the motion of our screw. There are a number of different measurement uncertainties which should be considered in this experiment. The first thing to consider was the battery's voltage, which was originally given at 1.5 volts. With the use of a multimeter, the true value was taken to be closer to 1.35 volts, with an uncertainty of plus or minus 10 millivolts. The second measurement uncertainty was that of the frame rate given by my iPhone 12 mini. The value given was 240 frames per second, with a measurement uncertainty of plus or minus 1 frame. Once these were taken into account, we could calculate the hertz of our electric motor, or revolutions per second, by counting the revolutions individually over a number of seconds in slow motion through slowing down the videos to 10%. This can be seen with the displayed videos here. Using this method, we got a series of results that are shown in this table here. This allowed us to estimate the motor to have 11.1 Hz, which is a lot lower than the 50 Hz of Australian mains power, but can be made sense of due to our simplistic design. Once the Hertz was found, the uncertainty could be calculated using the formula displayed below, with Hertz max minus Hertz min divided by 2, which gives us a rather large uncertainty of plus or minus 3.11 Hz. This makes sense considering the rather primitive nature of the experiment. Overall, we managed to successfully create an electric motor with the provided materials. We estimated it to rotate at 11.1 Hz, with an uncertainty of plus or minus 3.11 Hz. We also found the effect of flipping the magnetic poles in the direction of the battery, in which the rotation swapped for each orientation. We also found that if the magnet is removed from the system, it simply collapses entirely, with no force to hold it together. Thank you for listening. I hope you enjoyed and understood, and now understand the concept of an electric motor a bit better, and how it works.